Everything's fallen apart the last week.
They always forget my name or stuff, and so like after this soccer too. The equipment knows the train's almost over, so it's like, man, shut it down.
Seems like it. Okay, woo, back. All right, we had left off on this problem on Monday. So take another few minutes to kind of look through this, determining if you can figure out whether they're acidic, basic, or neutral. Hopefully the lab helped. It was supposed to kind of help with this, and then we'll talk about it. Come on, there we go. Well,
It is plugged in.
yeah, the charger's really finicky.
What page is it?
What do you mean, what page?
Like, I'm trying to find the slide.
Oh, it should be on the very, oh, I think it's page 5.
OneNote's not open on my end. PC just does not like OneNote.
It should, yeah, it should be sharing, and then. Did you find it on the left hand?
I got all of this from Megan, but I was wondering what you have for this one. 'Cause I haven't done it.
I was gonna say, I think your email, but I don't think I have your contact number, but did I give it back to you? It's sometimes like the grades don't save or.
I believe it's been on top of your binder.
It might be in the other room. I was looking for it. Yeah, otherwise, like, I don't mind, she always can't give me credit for it. Right here. Okay, yes, email it. Yeah.
I just haven't used it throughout. I didn't know it, but I've had this one. And then that one.
Oh, okay, well, let me put your grade in then. All right, do we still need more time with this? Yes, no? Confused? Are we kind of confused about this still? Yes, okay, so let's just start talking about it then. So walk me through strontium chloride here. So let's do our analysis. So what base is strontium kind of paired with? Kind of look at where it is, right? Don't overthink it. What do you notice about strontium, like where it is on the periodic table? So metal, which group is it?
Group A?
Group, which one?
Oh, 2A?
Yeah, so group 2, right? So it's a 2 plus group. So, right, group 2. And so then what bases do they tend to make? What base is it from? So what's the definition of a base? Yeah, produces hydroxide. So then kind of the simplest base is strontium hydroxide then. And then it's asking, okay, well, does it fully disassociate? But it's our group 2, right, ionic compound. So yes, fully disassociates. And so if it fully disassociates, that means our strontium then is neutral.
How do we know if it fully disassociates?
So this one, we just base it off of the ionic compound properties. So since it's just our group 2, so it follows our similar pattern of like magnesium hydroxide or calcium hydroxide. Oops, I got too many parentheses there. But all of those, right, just fully disassociate. Ionic compounds dissolve in solution.
So if it's an ionic compound, it dissolves in solution.
Yeah.
Fully disassociates.
So then we have that. And then, so let's look at our chlorine then. So what's our chlorine analysis, right? So then it asks, well, what acid does chlorine come with? What's it paired with? Remember, think simply. Oh, sorry. Oh, go away. Yeah, so HCl. So then is HCl a strong acid, weak acid? So strong.
So how did you figure that out, what it's paired with?
So that you just go by the definition, right? So then it's, the simplest one is just adding like a hydrogen to it to make it, acidic. So treating chloride, right, kind of like A minus. So then we're trying to figure out, well, what's HA? So then kind of sticking just a proton to it. And so good, everyone said it was strong. And so if it's strong, right, again, we're saying that this is not going to happen, right? So it can't do this. So I'm drawing out the mechanism, but, big old fat, oops, I put HF for some reason. HCl, so right, it's not going to reform hydrochloric acid because it's fully disassociated. So if this doesn't happen, right, chlorine is also neutral then.
The reason that I knew that HCl was strong as an acid is because of the lab today, it said it.
Yeah.
But how would I know if it's strong or weak?
So you might have to commit some of those acids to memory. Let's see. I think on page,
I would take a printout of that.
okay, yeah, I can get them while you're quizzing.
That would be great.
I'll do that for your quiz. But on here, it says the 6 strong acids.
Right, okay.
So these are kind of the main ones you'll encounter. So yeah, unfortunately, you just kind of have to know your strong acids. But then I'll give you this printout, and so this can kind of remind you of, oh yeah, these are my strong acids, right? They're not going to reform in water, right? So it's reminding us these do not undergo base ionization, so we can't make, right, hydrobromic, hydrochloric, hydroiodic, or sulfuric acid in solution. All right, so that means that strontium then, so right, strontium was neutral, chloride was neutral, so overall is neutral. So now try that analysis just for a second, right, with the aluminum bromide. And remember what we had said about aluminum, because that was something special. people think their grade is lower than what can happen. I'm like, oh, I'm passing. And then, yeah. Yeah, I don't fix the grades till the very end, unfortunately, for y'all. All right, what do we think about aluminum bromide here? So what do we remember about aluminum, though? So it's not a transition metal. It's over in our main group section, but it's still special.
Being a post-transition metal, or is that not?
So it's more main group, so it's over here in like, yeah, metalloids. We could call it post-transition, but what do we know about aluminum? What do we remember? There was some like rule for aluminum and metal species. I'll scroll back up. So it's on this same page. It was going through the rules. And remember this last one here? And it's part of this last one, right? So it says if it's a highly charged metal ion and blah, 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 right? The anion is, of course, just the conjugate base, but just focusing on our highly charged metal ion. So if we have a metal ion, then it tends to be acidic. So this is kind of a special one. So
It also said specifically if the salt's cation, right?
yeah, because it's going to be the cation, right? So usually, remember, this goes back to what I said, that cations are usually acidic, if anything. So they're going to be acidic or neutral. So cations are usually never basic. Yeah, so that's what that's kind of referring to.
Okay.
And so yes, this is our highly charged metal ion, and so these hydroxides can kind of clamp onto aluminum like this. But like I said, we won't go too into it because it's actually more detailed than this, but just know, all right, aluminum is acidic since it binds. What it ends up doing is it binds to the hydroxides, which leaves H+ ions in solution from water. And then what's bromine? Is it acidic, basic, neutral?
It says on your little chart, it said that it's acidic when it's paired with hydrogen, but it's just a negative charged ion.
For
The bromide or the,
yeah, so then what acid does it come from? So hydrobromic, and then so hydrobromic, is that strong or weak? So strong, so fully disassociates. So that means what for our bromine?
it's acidic.
So not the bromine itself, right? Because bromine can't do anything, so it can't reform the HBr. Yep, so then that leaves it as neutral for the bromine. And then that means overall, our aluminum bromide is acidic. And I'll just add right from the aluminum.
Would it be considered acidic
Because,
like the pH?
sorry, repeat your question.
If it makes it more acidic
Yeah, so what this is saying is like, okay, because what it's asking is like, what happens in water? And so, yeah, what it's saying, okay, we have aluminum bromide and water. And then, so like I was kind of showing with my bad drawings, is you get some sort of like pairing here with the water initially, but then one of these hydrogens can float off, so then that leaves you with the aluminum hydroxide and then H plus in solution. And then, yeah, by the definition of an acid being something that leaves H plus ions in solution, aluminum is acidic. So that's where the H plus ions are coming from, and then the hydroxides are complexed to the aluminum. Because aluminum can actually have like 6 waters on it, or hydroxides, but like I said, I didn't want to get fully into it because aluminum does weird stuff, but yeah, that's kind of the gist of it. Does that clarify?
Yeah.
All right, so then see if you can try C on your own, but right, don't let this funny thing throw you off. So let me rewrite it for you. So C is CH3, NH3, and I forgot that counter ion. So see if you can decode that. What is this weird thing too? Yeah, and again, just glancing at grades, I don't think anyone in here is in danger of failing or anything, right? I'm not looking to fail anybody, so just turn in all your assignments, just keep it up, right? Take the final, and you should be fine. That's kind of the point. So I don't want people stressing out.
I'm so glad you just said that because I'm sitting here like.
Just turn in as many things as you can, as complete as possible, and I accept late work. Like pretty much, actually, you could email me because grades are due on Monday. If you emailed me at like Sunday at 5 p.m., I'd probably take it. Grades are due at midnight, so that starts to get, you know, a little on the deadline. But yeah, I'm very lenient. I'd much rather.
This Monday,
Oh, no, not this Monday. Sorry, next Monday. Right? Let me pull up the calendar.
Next Monday. The 17th.
Yeah, whenever grades are due. So they're due at noon on the 17th for me. But I will take stuff even if you're emailing me like over the weekend. You know, like I do not care. I want it in as opposed to anything else.
Sorry, maybe what's like the bonus thing?
Oh, there's no bonus, or, I think what's gonna happen, because, like I said, I'm not worried about anyone in here, and probably for our bonus, it'll end up being the Earth Day project that y'all did, right? Everybody did a great job, so that'll probably just go into bonuses, but,
So, is it like, would it be out of 110, or is it out of 100?
don't worry about it. You're gonna stress yourself out, don't worry about it. I do grade normalization at the end, it doesn't matter, right? Everything's just gonna be normalized. All right, how did this go? Did we figure out what this weird looking thing was at the beginning? It should remind you of something, another compound. And it was also my other hint that we only have this sort of type of cation that's acidic. So some sort of, well, this is nitrate over here. But this is a nitrogen thing, but what's our other nitrogen thing? Ammonium. Yeah, so ammonium and ammonia, right? So it should remind you of ammonium, NH4 plus. And we can draw this out. So this is methylamine again. So going back to Breaking Bad and drug references. But, right, it doesn't matter what this thing is or what it's attached to. We're just kind of noticing that we have a nitrogen, and then there should be like 2 hydrogens attached to it at least. So that's where we get our R group. And so, yeah, this is just methyl ammonium then. And so if we know, what do we remember about ammonium? Is it acidic, basic, neutral? Oh, other way. Yeah, acidic. So if this is acidic, then all its other derivative families are also acidic. So this funky thing, our methylammonium, is also acidic then. And again, right, it would just display the same behavior as our ammonium. Yeah.
My thinking around looking at that, because I didn't draw the same conclusions, but I saw that there were a lot of hydrogens involved with it, so I figured it would be a donor.
Yeah, that's,
Is that another good way to think of it?
yeah, because you're kind of looking, who has protons to donate type of thing, so that's a good,
So when you're figuring out, you always wanna like add it to water.
yeah.
And see if it's acidic, basic, or neutral.
Yeah, so that's what we're doing with the salts. And that's, again, kind of what you did in lab today with the pH testing, right? You tested the sodium acetate, you did the ammonia, and then you did the ammonium chloride. So hopefully kind of gave you a sense. So then, yeah, you would remake our methylamine here. Oops, sorry, I left off the hydrogen. Oh. No, too many now, sorry. And then there's our hydronium formed. Yay. And then what was nitrate again? Is this acidic, basic, neutral? Where did nitrate come from? So what acid? Well then, because it also makes, right, HNO3 though. So what's that? Which acid?
You mean like a strong acid?
Yeah, is it a strong acid then?
Yeah.
So it is, do you know what the name of this strong acid is? Nitric. Yeah, so remember, you just have to kind of memorize your acid naming. But yeah, this is nitric acid. And then if we've forgotten, oh, we have our nitrate, right? And then it tells us, oh, it does not undergo base ionization. And then, oh, there's our nitric acid corresponding. And, right, reminding us complete acid ionization. And then, oh, this one, NaCHO2. So see if you can do that one. Yeah, nachos. Now that just makes me want nachos, right? So what do we think about this one? So let's start with sodium. So what's sodium? Is it acidic, basic, neutral? Acidic. Basic. What base does it come from? Well, what's its base derivative? So how do you make it a base, right? Add hydroxides. What base is that, though? Yeah, so NaOH, but then what do we know about sodium hydroxide? Strong base, weak base? What do we say? Yeah, it's a strong base, right? It's just an ionic compound, fully disassociates. So then what does that make our sodium? Acidic, basic, neutral? What do we say? But it can't reform, right? So it comes from its base form, but then the sodium itself, yeah, so the sodium is neutral, so it can't reform the base or anything. It can't. Basically, right, we're saying you put sodium in water and it doesn't make a base, right? It doesn't reform sodium hydroxide and leave H plus ions. It doesn't do anything. It just, stares at the water. Yeah, so cations will either be acidic or neutral. Yeah, so cations, yeah, they're not always acidic, but if they're going to be anything, they'll be acidic.
So if it's a strong acid or base, if it completely dissociates in water, but if it doesn't reform?
Yeah, so if it completely disassociates, that means that it's not going to reform, right?
That means it's not going to.
Yeah. And so, because that's the question that we're asking is like, if we put just sodium and water, will it make sodium hydroxide? Will it do that? But then, we know, well, it doesn't, because then your sodium chloride salt would be basic. And then what's this CHO2 thing? And so my recommendation would probably be to look at this chart too. This could help you get some inspiration. So do you see the acid form of that, the nacho ending on there? The CHO2. Yeah, so formic acid. And so now that we're reading it off this chart, though, this makes it easier, right? Formic acid, well, yeah, so it's obviously a weak acid, but okay, but let's slow down there, right? So formic acid itself is an acid, but then we're saying, right, formate. So what happens with formate, though? Because remember, formate's going to be a base. So then you have this little CH. So this is formate, right? So it's hanging out. And then we're saying, well, what happens when it's in water? But then, again, going back to here, so we see equilibrium process. So this can reform. But this reaction, right, isn't quite the same of what we're looking at. So it's a little bit different. And so now we're saying that our formate is going to deprotonate our water, right, reform formic acid. So there's our formic acid again, but then we are left with hydroxide, right? So it formed hydroxide ions in solution. So what does that make formate here? It makes hydroxide. So what's the definition of a base? Yeah, so it makes hydroxide, so that means that our formate is basic. So the CHO2 is basic. Does that make sense to everybody, what happened there? So let's kind of review, right? So we looked at our formic acid, and then just compare the different reactions, right? Because this is showing your formic acid in water, and it's showing, right, that deprotonation to form hydronium and formate. And then we're kind of doing the opposite, right? So then we're taking the formate in water, so not just the full reverse, and then that's what gives us our hydroxide, because again, we deprotonated the water. So that's always kind of what you got to do, right? You reframe it, so now you're just taking the formate, reacting it with water, and seeing what happens. So then that makes this one overall basic, since our sodium was neutral. And then we'll probably skip this last one, just because, so they kind of gave us the answer up here, but we probably won't do this just for our, sake of Chem 104, since then you have to calculate the KB and KBA and blah, blah, blah. So I won't have you compare salts that are acidic and basic, right? So this one, so blah, 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 we can see that it would be acidic, but we're just not going to go there because we have to compare acid and base strengths. All right, do we feel okay about the rest of them, kind of A through D, maybe making more sense? So let's look at some other stuff. Let's actually look at, so this is the solutions homework. I just wanted to talk about it briefly, since I think some people had some questions, and I noticed people were getting stuff wrong on like the homework and other stuff. And so let's look at 8 and kind of what we're supposed to do. And it says, determine the number of particles contained in 1 mole of each solute, and then rank our solutions. And so what I would start with is the first thing we should do is figure out our true effective molarity, right? So this is just how much we made of our solution, but then we need to answer, well, how many particles does it disassociate into, and what's its effective molarity? So let's just do that. So for sucrose, does it disassociate? So no. So it's still, right, 0.1 molar solution of sucrose. So that's fine. What about sodium chloride? Does that disassociate? So yes, and then how many particles will we get from this sodium chloride? So 2. So now we can multiply this 0.08 molarity times 2. So we effectively have a 0.16 molar solution of ions, right? Does that make sense to everybody? And then the next one, so what about magnesium chloride? How many particles would this disassociate into? Let's see. So 3, right? So 1 magnesium, 2 chloride, so then times 3. So we have a 0.09 molar effective solution of ions. All right, so now we can rank them. And so basically now that we have them ranked, then you just kind of flip their orders back and forth since we go by their effective molarity. So who has the highest vapor pressure? Sorry, which one? So increasing vapor pressure, though. So remember, it's boiling point elevation. And this always gets confusing, too, right? So we have boiling point elevation. And so that means, right, more molecules is decreased vapor pressure. So then we could say, so sodium chloride is actually the lowest. So, right, this has the highest boiling point then, and maybe this helps us with 9. So 8.
And you said more molecules is decreasing the?
Other way. So more molecules increases. So boiling point elevation, and then freezing point depression. So it goes the extremes. So maybe let's do boiling point. So yeah, so then our sodium chloride has the highest boiling point since it has the most ions. Sucrose would be in the middle, since it, right, is in the middle molarity-wise. And then magnesium chloride is at the end. And so then vapor pressure would be the opposite, so sucrose in the middle. Magnesium chloride still has the highest vapor pressure since it has the lowest amount of ions. And then, of course, we can continue. I'll do the freezing point, so then freezing point. So increasing freezing point, we have freezing point depression. So the lowest will be sodium chloride. Sucrose in the middle, of course, and then magnesium chloride at the end. And so once you have them with their effective molarities as well, it's pretty simple, right? Nothing's changed in the ordering. We just kind of flip them depending. And then, of course, sodium chloride has the highest osmotic pressure since it's just based on our effective molarity, so MRT. And then magnesium chloride at the end. Let's talk about other things. So I want to do a stoichiometry worksheet, yeah.
I have a question first. How do you know that the sucrose doesn't dissociate?
Oh, we just have to know that from just the structure of sucrose. So, right, you have to know that sucrose is a molecule then, so basically not an ionic compound, so it doesn't dissociate. And these were ionic compounds, so we know those dissociate.
So all acids and bases are ionic compounds?
Well, the strong bases are ionic compounds, but then, right, you can have organic acids, so you can't make that generalization. Let's look at something else. See if I can remember the problem. Yep, here's the problem. So this was on your quiz, your take-home quiz. And it says something that the mass of 12 liters of carbon monoxide at STP is I think this is the first person who's done it, what I was looking for. And so what most people did, and this was fine, it still got you the right answer, but they did some sort of PV equals nRT. And then I did notice that some people were using the wrong R. So remember, R is 0.0821, and that's for ATM, liters, kelvins, moles. So some people are using the 8.3 something. I can't remember the other constant, but this is for energy, when you have the R constant in energy. So they both are, and they're both gas constants. They're just different situations. So make sure you're plugging in this one for PV equals nRT. So that threw off some people. But then the PV equals nRT method, while this isn't wrong, a lot of people are doing way more work than what I was going for with this problem. And so kind of the shortcut is it's at STP, and then it's asking for mass, right? We know that STP is just by definition, right? 1 mole is 22.4 liters at STP. So then the easiest way to do this, at least what I was going for, is then you can set up a proportion. So we have 12 liters of CO at STP. And so let's set up our proportion. So then we know at STP 22.4 liters, well, we can figure out the mass, right? So that would just be the molecular weight of CO. So that's what I wrote for a lot of people on your quiz, is I wrote something like that, and I was like too lazy to solve it. But then we can solve it and go over numbers more precisely. So then CO, right, the molecular weight should be something, so 12 plus 16 roughly. Again, you could have different values, but you have 28 then for your molecular weight. So now we can plug this in.
And where do you get the 16 from? Cause
Oxygen, yeah, I just rounded. So I was kind of doing quick and dirty to show you the method. So then you have your molecular weight of whatever you're interested in at STP. So now we can plug in 28 grams per mole. Now we can do our cross multiplication to figure out how much 12 liters weighs. So now 12 times 28 divided by 22.4, and that gives you 15. So many people still got this 15 grams, but like I said, y'all went about it kind of the harder method, and I just wanted to show that shortcut. And so let's do some practice in the time we have. And so now we want to combine, right, our solutions, stoichiometry, and everything. So this should be kind of similar to your lab, but let's try this one together.
did we get that worksheet or is it just one that you have on there?
No, it's just one that I put on there. I could print it for you. I steal them from Everett Community College, but sometimes their answer keys are wrong, so I don't guarantee their answer key. But they have good practice problems.
I just wanna make sure it wasn't like a missing thing I didn't have and I was like, oh, sorry.
No, but let's try this out. So we're given the equation. So magnesium hydroxide plus 2 equivalents of hydrobromic acid give us our neutralization. Oops, I gave that away. But let's look at number 2 then. So how many milliliters of 0.225 molarity hydrobromic acid would be needed to react with 3.26 grams of magnesium hydroxide? So how's number 2 going? What have we done so far? So it's asking for how many milliliters. And then what can we solve then? What do we need? So I don't think we need the HBr molecular weight just because we have the molarity. But what do we need the molecular weight of? Yeah, so do we get that molecular weight? Any takers? Any masses?
What's polarity again? Is it
Moles over liters. So what's our molecular weight of magnesium hydroxide? So we could add it up, right? What's magnesium? 24.35 plus 2 hydroxide, so 17 times 2 roughly. Yeah, so something like 58.3 or, again, could be something else. So 58.3 grams roughly per mole. So then what do we do with this information?
Would you set up the equation like you did before?
What do you mean?
Like with the mass of the 12 liters of the, at the STP, kind of like that, or is it a whole different equation with the moles?
Yeah, so what do we want to solve for, though? What are we going for? What do we need? So we want milliliters, but how do we get to milliliters, right? Because we don't even have moles of HBr yet. So how do we find that? What can we find moles of? We have it, right? We have grams of magnesium hydroxide. We have the molecular weight. So we can get moles, right? You guys are kind of scaring me a little. Right, so then we can do our moles. So 3.26 grams of magnesium hydroxide. So this is just what we're starting with. Then divide it by our molecular weight. So 58.3 grams on bottom, mole goes on top. So let's just divide that, so 58.3. And so then that gives us moles of magnesium hydroxide, so about 0.0559. So moles of magnesium hydroxide. So now what do? We have our balanced equation.
So we have to change to milliliters?
So we're still not quite there yet because we're at moles, right? But
Do we set the, remember we just got equal to the molarity of whatever it is, the HBr, and then solve for liters and then convert that to milliliters?
almost, we're just skipping one little step, right? So we have go back to our balanced equation, right? So we figured out moles of magnesium hydroxide. But then what's the problem with this equation? So how many moles of magnesium hydroxide do you have to HBr? So it's a 1:2 ratio, right? So we can't just skip ahead yet. So first we have to do the mole-mole ratio. So let's do that. So we need moles of HBr. So we can set up our mole-mole ratio. So I'll put 2 moles of HBr on top, and then 1 mole of magnesium hydroxide on bottom. So then, right, we need twice as many moles of HBr as we do magnesium hydroxide. So now times 2. So now we have 0.112 moles of hydrobromic acid. So now we're ready to do what you said. So right now that we have moles, now we can set it up with our molarity. So we can set up our 0.225 molarity. So now we're saying, okay, let's say our stockroom had given us a 0.225 molar solution of HBr. Right now we would figure out how many milliliters we need.
So
Yeah.
when dealing with molarity, instead of writing moles, we write molar? Or is that, why do you write molar instead of mole?
Well, it's moles per liter, so I could write moles per liter, but I'm trying to figure out basically how much I need. So I don't know if it's maybe better if I write it so 0.255 moles, right, in 1 liter. I don't know if that helps to kind of see it better. So then we're saying, well, I need 0.112 moles. So how much do I need? So it's the same thing, right? It's just which is kind of easier for your brain. And so now we can cross multiply. So 0.112 then divided by 0.225. And then remember the answer is going to be in liters. So now X is 0.498, I'll just round, so 0.498 liters, but it's asking for milliliters, so about 498 milliliters. Questions about that one? And just as a caveat, I noticed this. So this is what I mean by I didn't make these sheets and I can't guarantee the answers. And so if you look at the answer that's listed, there's a typo in their own answer key. So they wrote in their own problem 225 and then the answer key is 255. So that accounts for the discrepancy. So just, if you're looking at that later, I wanted to point that out. All right, do we want to keep going with 3? Do we want to take a quiz? How are we feeling? I also have the demo, which I didn't do, which we could do the demo as well. I'm just kind of trying to feel out where y'all are.
And what is this demonstrating?
So I at least wanted to compare, so we have 4 molar acetic acid, and then I wanted to compare it with hydrochloric acid. So let's see how this goes.
See if the stockroom mixed it correct.
Well, this one should be correct because I just pulled it from the stock bottles. And so the point is, let's see, so I'll do the HCl first. So nice and bright, right? Fully disassociated in solution, so that's why it's bright. And let me not shock myself. And so let's try the acetic acid. And so see how it's weaker? So it's a little less bright. And I'm glad that worked out. So I'll tell you the secret. So this is 4 molar acetic acid versus 3 molar hydrochloric. So if I had gotten, an even stronger acid, it might have been a little bit more bright. But the stockroom did not have 4 molar HCl ready to go.
And what was the second one?
Acetic acid. So we have 4 molar acetic acid and then 3 molar HCl. So I'll do it again, right? So you can again just appreciate how bright the HCl is, since it's a strong acid, completely disassociated, versus, I'll wipe it off so I don't contaminate, versus our acetic acid, weak acid, stronger molarity, but weaker bulb. So that was all I wanted to show for the demo. Unless you wanted to play with anything. So how are we feeling? Do we want to just go ahead and take the quiz and then maybe people ask questions, or do we have other things that we should go over as a class? No, your quiz this week is over the solution stuff from last week. So like some definition stuff, dilutions, a lot of vocabulary. Oh, question?
It's still about like the homework. I don't.
Is it the solution homework?
Yeah, I don't get how you get the osmotic like pressure, like which is increasing. Like the other two, it makes sense. Like the
Oh, so
freezing and boiling point, I think, but
the osmotic pressure was just based on the number of particles. So more particles, greater osmotic pressure.
okay, so the period is would be
Yeah. All right, other questions? Should we go over stuff as a class or not? All right, I think I'll just hand out the quiz. With that being said, right, ask me questions if you need help on stuff, on labs or anything. Don't be shy. I'll just get the quiz going so people.
I was gonna see if I could send this in on Monday, so I could run home and check on my brother.
Yeah, that'll be okay. Yeah, or if you,
I have class at 3, so I could always just do it and then bring it back.
yeah, I was gonna say, or like email it to me, but yeah, Monday is okay, works great.
Would I just take a picture and send it to you if I were to email it to you? Okay. That'll probably be easier.
So for that one, yeah, what did you end up for your data? Yeah, we'll just run with it, because you get at least got like someone capable is 21.
Okay.
Yeah, because, like I said, we saw that Cammie got something unreasonable.
It's always me, what?
Stop it. The outlier voice. It wasn't your
Science
fault,
doesn't
though. We
like me.
proved it.
I almost